Hello everybody and welcome to the course on optimization techniques for digital VLSI design. This is a 8 weeks course and it will be taken by my colleague Chandan Karfa and myself. I am Santosh Biswas. So welcome to this course and this is the introductory lecture. Right. So basically what we are going to expect in this course, as you can see from the title, that this is saying about optimization techniques for VLSI design. So what do you mean by optimization? Actually, in a very raw language, if I want to tell, optimization means you want to get maximum benefits from minimum resources, that is minimum work, maximum satisfaction, which is actually a very idealistic and non-practical goal. So in all domains of engineering or even all domains of our life, we always work for optimization, that we have some given set of resources and we want to get the maximum benefit out of it. In this course, we have two main terms, optimization and digital design. So what digital design, we have all done this course in our undergraduate level. This is basically a simple kind of implementation of hardware, in which case you have some inputs in binary form and the outputs you will also get in some terms of binary numbers. Basically you will have to design some kind of circuits which can process given a digital input and you can get a digital output. So in a quote unquote, this is your digital design. Now basically what I want to optimize. So there are three basic things you have to optimize. First thing, I should be able to process this input at extremely fast rate. So it should have a gigahertz, megahertz, gigahertz, or even very high, extremely high frequency I want, so that you can process the data in the click, just in a click. We want very low area overhead. Why? Because more area overhead you have, larger your circuit will be and you have more cost. So you want a very less area overhead circuit to do the same purpose, and as well at the same time we nowadays are talking about power. So basically you have a three part corner optimization problem: area, power and speed. And so why about power? Because nowadays most of the devices are handheld, so you want a low power for them, because if you have a higher power requirement, then batteries will go down and you will have a lower battery backup, which is one of the most critical requirement nowadays we all feel while using the mobile phones, because smartphones have lot of functionalities, but you see that every time in one day or multiple times we have to charge it. Say for example, somebody can give you a mobile phone with lot of functionalities as well as 7 days battery backup. I think that will be the taker of the market. So basically these are three things we want to optimize. We want a low area, low power and extremely high speed circuit, and of course put as much functionality as we can. So this is about optimization of the VLSI circuits. Now there is another way of looking at it. How do you design it? So you have a circuit, you have a specification, rather I should say a specification. Now you have to design a circuit so that it has low power, low speed and low area. So if I talk about digital design, there are two ways of looking at it. One way is to optimize the designs so that you have low power, low area, low speed, and another way is that how we can design efficient or optimized VLSI circuits. So in this course basically we are going to look at the other angle, that what are the tools or what are the angles or how we can theoretically automate the solving of digital circuit problems so that they are actually optimized in terms of area, power and speed. So one is the circuit itself that can be optimized, and another is that as the circuits are quite large nowadays, extremely complex, as we will see in the introductory lecture. So you cannot design the circuits manually. You can design a 2-bit counter, you can design an adder, you can design a multiplexer, you can design a simple lift elevator controller, as we have already done in the second year digital design course. That can be done manually. But if I say that you design a scientific calculator, the whole processor you design. So it is extremely difficult or almost impossible to design this by hand. Now think of complex circuits like a processor, multi-core architecture, network on chip, SoCs. It is almost impossible to design any of these stuffs manually. So basically only the functional requirements and basic top level decisions are made manually. After that there is a CAD tool, we call it, actually you might have heard the name, called CAD for VLSI. So there are huge amount of CAD tools which basically automate this flow. So now goal of this CAD flow is to generate an optimized VLSI circuit, digital circuit, which has low area, low power and high speed. But again that tool also has to be optimized, because if the tool takes 100 years to generate a circuit, that is not going to solve our purpose. So larger the circuit becomes or more complicated specification is there, larger is the amount of time the CAD tools will take to solve or give you circuit output. So those CAD algorithms also have to be optimized, so that you can handle very large and complex systems in a very small amount of time. basically this course looks at this angle of optimization. So basically this course you can also call as optimization for CAD for VLSI. So CAD for VLSI is a very well known subject, lot of courses are available in the market, but they are generally looking at reasonably low complex circuits. If you look at the traditional CAD for VLSI courses which are available in the internet or the textbooks, they handle circuits which are reasonably complex. But once you go for multi-core architecture, network on chip and SoCs, those traditional CAD algorithms will take very long time to solve or design circuits if they are very complex, or they will lead to infeasible timing requirements in order to solve them. So in this course basically we are going to mainly look at the optimization techniques so that we can design good CAD architecture or good CAD algorithms so that we can solve the circuit design more faster, or circuit design can be generated more fast. But as I have already told you, that initial part, because everything cannot be automated, if everything is automated there will be no requirement of engineers like us, but the initial specification, that what you want to do, the basic hand architecture for the broad block level diagram of the circuit has to be done manually. So and those will be automatically synthesized to circuits. So if you give an improper kind of inputs to the CAD tools, they will generate improper outputs. So on one angle we have to optimize the CAD algorithm so that they can solve the problems in a faster manner, as well as the same time the first few stages of the design flow has to be done manually, and there also you have to optimize. So our tool will be something like, so this is one part which is manual, which actually is how to design the circuit broad level specification and broad level block diagrams. Here you actually optimize. After that there is a CAD flow. So which automatically there is this broad level diagrams or broad level circuit level diagrams, and automatically generate the layout of the circuit. So this part of the CAD tool basically is automated. So now, so that they can generate optimized circuits with low area, low power and high speed circuit as much as possible. So there are automatic tools which will do that. Now in this part of the design flow we will try to optimize the CAD algorithm. The CAD algorithms we are going to try to optimize so that we can solve, given a manual specification and block level diagram of the circuits, we want to quickly come to the layout, so that solving is done automatically with the help of algorithms. That part we want to have optimized algorithms to do that. So our optimization course will be divided in this part. So this introductory slide, if you can see, basically tells that nowadays how the circuit complexity have increased from small scale integration to medium scale integration, then to VLSI, which is the current term right now, but in fact nowadays we are also calling the term called ultra large scale integration. So if you are talking about NOCs and SOCs, they are ultra large scale integration. So our CAD for flow optimization, which we will be mainly learning in this course, will cater to design of ultra large scale circuits. So very large number of components are now fabricated, so you have system on chips, network on chips and whatnot. But anyway, all these things basically are automated by CAD tools. You cannot design a NOC manually. So you will have a larger diagram, you tell what are the core you require, what are the functionalities in very broad level language like C, and then automatically the CAD tool will generate the circuit for you. But of course, if you are giving but as a human being you have to tell what is the specification of the circuit, at the same time you have to also tell about the broad level block diagram of the circuit. Like as I told you, the specification you have to write in terms of high level language like C, system Verilog, etc. So there is a manual part. So there if you are there no because that is an art. No automation can design an art. So art is basically the power or intelligence of the engineer. So there are a lot of optimization tools, optimization techniques rather. So if you are given a system specification and if you do not follow those optimization techniques, then you may give a very wrong kind of input to the CAD tools. So even if your CAD tools are optimized to solve the problem in a very fast manner, but still you are going to get a very bad quality circuit in terms of maybe high area, high power and low speed. So input also has to be properly justified or properly optimized. So our course will be mainly looking at this. Anyway, so let us go ahead and then I will see. So now say for example the circuit is there, there is a you are very intelligent engineer, you have given very nice block level diagrams and your CAD tool is also very much optimized. So you get a very nice circuit with low area, low power and high speed in a very quick processing time, because everything is optimized, input and also the CAD tool flow. But again, how do you know the design is whatever you intended is correct? Because you will give inputs as some high level language like system C or system Verilog, and finally you are going to get something as a physical layout, that is the transistors. How do you know that everything has been operated properly, that your design from system specification to layout, whether all the things are equivalently translated or not? See, I said that I want to design a plus B, finally adder. Finally, I have got a layout for the adder. How do I know the transistor level implementation exactly is equivalent to your adder implementation or not? Therefore, even it is said that automated tools like CAD tools also may have bugs, because the CAD tools are huge large amount of software which has been coded by engineers like you and me. So, they can also have bugs. So, how do I know that whatever I have designed or whatever is coming at the transistor level is same as what I intended to design? So, there is something called formal verification, because if I try to check all possible input conditions, it is almost impossible, because you can think that I have say 100, I have a 128 bit adder. So, all possible input combinations will be 2 to the power 128 plus 128 plus 1 bit carry, exponential problem. You can never solve that in a reasonable amount of time. So, we have to check it formally. Formally means we have to have state based modeling, and mathematically you have to verify that whatever input I have given as specification, the same thing has been implemented in the transistor level or at the gate level. At each intermediate translation stage, you have to verify it. So, that is called actually verification. That is also a very important part in case of VLSI design. So, in this course, one full module will be dedicated that how we can go for formal verification of reasonably complex circuits. Because if you look at the CAD algorithms, CAD textbook or which is on CAD for VLSI, you will find very preliminary topics like binary decision diagram, LTL and CTL based model checking, etc. But in this course, we will slightly jump above that and we will see how we can formally verify circuits which are slightly at a much higher level, and we will do it by abstraction. But anyway, that is one direction we have to solve. Finally, there is something called testing, because it is a very interesting thing about VLSI circuits that whenever we fabricate a circuit, we are actually using a very complex fabrication technology. So, the yield is actually not very high. So, yield is something around say maybe 60 to 70%. That is, out of 100 devices fabricated, maybe you are having 70 devices normal and 30 will have defects. Now, what I will do? Will I repair them? No. In VLSI, we do not repair basically. What we do? We throw the 30 devices out and send the 70 to the market, and profit is made by basically increasing the cost. And we always want to do that, because the higher technology you go for fabrication, more functionalities you can get, we can give in the circuit, and there will be more market capture you can do. But if you say that I want to make a very nice stable technology and I do not want to have any faults, then you will be lagged behind, because many other companies or vendors will come before you and they will capture the market. So, what is the idea? I will use a very sophisticated fabrication technology. No problem, even if my yield is 60 to 70%, I will throw the bad chips in a bin and good chips I will sell to the market and increase the profit by increasing the cost. So, there are takers. But again, if your yield is around 60 to 70%, you have to be very careful. All the devices which has been fabricated have to be tested. Bad one you have to throw and good one you have to ship. But if the fabrication technology say that 99.9999% yield is there, then you know that almost every device is normal. Just with the preliminary testing, you can ship it to the market, because you know that 1 in 1 million chip will be defective, so that I can easily replace. But here you cannot do, because around 30% customers will have a defective chip and you will be out of the market if you do that. So, therefore, testing is also very important paradigm of VLSI design. So, there is now again here one slight difference between integration between verification and test is there. Verification means you have to do it formally, and this is a software based approach, that you have a circuit design which is you have designed at specification level, and you have the which I call actually layout of the transistor level layout. So, which is the GDS2 file, actually if you know by the industry term we call it GDS file. So, which will actually give you the configuration of the layout. So, now you can verify whether this GDS file, that is your transistor level implementation, actually formally matches the specification or not. Both are at the software level, and you have to do it only once, because after that things are going to be made in hardware. So, there are two versions of software. One version you say that is the high level implementation of your circuit in terms of block diagram, one is the low level implementation in transistor. You just want to see whether they are formally matching or not. So, verification has to be done once and it is a software case. But in testing, what happens? Now, your fabrication has been done and 1,000 million chips have been fabricated. Now, you want to find out whether there are any defects in the circuit due to fabrication, because formal verification has proved that whatever you wanted to design at the high level is implemented in the transistor level. Now, there can be defects while fabricating it. It is not a design problem, it is a fabrication problem or a manufacturing problem. Then what do you have to verify? Then basically all the chips has to be tested. That is the difference between testing and verification. Now, testing means a physical device is there, you have to apply inputs and all the device has to be tested. So, you can understand that if I have to apply one extra test pattern, then one extra test pattern has to be applied to all the 1 million devices. If I can reduce one test pattern, then actually 1 million devices will have a lower test time. So, it is very important to optimize how I can optimize the amount of tests. that how I can reduce test time, or how can I have design can have good automated test pattern generation, so that I can quickly generate good quality test patterns. So basically this is what is the typical VLSI design flow. We have design intent, then we make the block diagrams, then basically there is some automatic tools which will give you the circuit gate level transistor level implementation, and then you fabricate and send it to the market. But now as this process is extremely complicated, we will always put automatic CAD tools to do that. So finally we have to verify it, and finally have to test it, so that we can give good chips to the market. So again repeating, optimization are at two levels. One level is you should have good specification, optimized specification, and optimized high level diagrams implementation, so that the tools can because the tools cannot do any magic, the CAD tools cannot do any magic. If you give good quality inputs, it will give good quality circuits or optimized circuits at the output. So you have to give optimal inputs to the CAD tool, and of course the CAD tool itself should be optimized, so that you are going to get very good tools, very good circuits at a reasonable amount of time. So there also have to do some optimization, and finally when your chips will be out in the market, basically you have to test them physically, so that you do not by chance ship some defective parts. So here what can be the optimization techniques? Of course the CAD tool which will generate the test patterns for you should be extremely fast, so that optimization also you should do, and finally the good quality test pattern should also be such that they do not take too much amount of time to test it, so that you can test more number of physical devices in a lower amount of time. Now we will go into more depth of the introductory part. So we call it digital design verification and test flow. In fact you can also call it CAD for VLSI. So you can see the first phase is actually called specification, that is manual, and architecture level synthesis. So this is a manual specification, there is a customer requirement, and then you know how to develop a specification, because the vendor or the customer will tell in a very non-technical language. They may say that I need a processor so that it can do image processing, it can do video game playing, this, that, and you design it for me. Then as an engineer you have to model it using what can be synthesized as hardware, how to be the block level implementation. Say somebody says that I want to design a calculator, you have to tell that it's a scientific calculator, business calculator, then what will be the adder, there will be a multiplier, there will be a subtractor, what will be the keyboard looking like. So all these specifications you have to design manually, and you have to give high level block diagrams. Now you can say that this will be an adder. After that everybody knows how an adder is to be implemented, and there are automatic tools which will do it for you. But exactly you require a serial adder, or you look a carry look ahead adder, or you want to implement multiplier by using adders, that nobody can automatically do it. That is actually called specification, and high level design block diagram is a manual procedure. So you have to give good quality inputs to the, after that we can say that these are all CAD tools. So you say that given the specification you have very nicely designed the block level diagram, how it should be implemented. So this RTL is done, that is given to you. Then there is some called architecture synthesis or high level synthesis. I will tell an example of that. That will basically try to map your blocks to real hardware, but at an abstract level. Then basically this is called the front end. So they will convert this diagram. Basically sometimes people also call that, people also say that there is some, this part is some manual intervention is still required for this. When you call architecture synthesis or high level synthesis, there are some helping tools are there, like high level compilers are there, some tools are available, but some manual intervention is also required to design architecture synthesis or somewhat hardware level implement or hardware level details of the specification, because specification can be English, it can be manual, it can be a layman language. But when you are saying architecture synthesis or high level synthesis, we are actually telling in terms of block level diagrams, what will be the functionalities, how will you implement. So there are some tools to do it, as well as basically there are some manual intervention is also required, because this is an art. But once you tell that this is the adder, this is the subtractor, this will be multiplier, I will do it in this fashion. So overall if the block diagrams are told, then you can automatically have as is a digital design, because everybody knows how to design an adder. There are automatic methods you know in digital design how to synthesize a counter. So if you say that I require a counter here, I require a comparator here, I require some block diagram here, that can be just in one flow. Automatic it can be generated, because we know that by solving Karnaugh maps, Queen-McClellan's method, how a adder can be implemented, how a counter can be implemented. So all these basic block diagrams can be easily synthesized. So basically what is this part we actually call the front end, which will take your block diagrams, make a register transfer level design, and from that they will make the gate level implementation. This is a full-fledged CAD flow, because of course we know that Karnaugh map can generally solve up to 5 variables, Queen-McClellan's still can extend it at some more number of variables, but in case of circuits there will be more than 1000 variables, or even much larger than that. Then there are optimized tools which are actually algorithm is called espresso, which is a heuristic which actually solves this in a much faster manner. Because if this is one, let me now come to an example of optimization. So this part, when I am telling you about manual, customer requires two high level diagrams, that you require an adder, you require a ripple carrier adder or multiplier or subtractor is an art. So given a problem to solve, what is the minimum number of circuits required to solve it in a reasonable amount of time? Say for example, for some operation I require 20 adders to do it. But say that I have lot of time because I do not require that amount of speed. So you can use 5 adders and then you can use it in 2 steps to solve the problem. But if you want a super fast design, then you have to have 10 parallel adders. So this part is fully manual, or very little CAD can come in there. So this is, in this idea, what is optimization here? That this is a engineer's intuitive optimization, that given the requirement of speed, area and power, how we can design the circuit in a block level. Now, so there is no CAD involved here. So we will also see basic design styles which can give you good quality inputs. So if you give a very bad quality input to the CAD tool to design, you are going to get a very inefficient circuit. So here optimization will be how I can have very nice, how I can from my intelligence, how I can solve the given problem in a more optimized manner, because you know your design specification, that what is the speed you have to achieve, what is the power requirement and what is the area requirement you have, and what is the price I am going to put in the market. Say that I can design a very super fast adder, I can do it in very low power maybe, and I can also have all other requirements, but then the cost of the chip may be very large, you will not have any customer. So you have to think based on the price and optimize and all the other parameters, what is the minimum amount of blocks I require to solve the problem. So here there will be some design optimization which I have to do. Once that is done, more or less all other parts are full of algorithms. Like if I have a Carnot map given to you or a Boolean function given to you, how can you have them implement in terms of minimum number of gates? You can use Carnot map, you can use Quine-McCleskey's algorithm, or for example you want to implement a counter. We know that we have present state is there, next state is there, then we go for a finite state machine level implementation. But all these things can be written as a code. So that is nothing but your CAD for VLSI. So there are a lot of CAD tools to solve the problem. But only thing is that now the numbers, input variables are not 4 or 5, they are hundreds and thousands. So how to solve it? Actually, if you look at any standard CAD for VLSI course, there are a lot of algorithms known like Espresso, which actually solves Boolean function optimization in a very less amount of time. Of course, the optimization quality may not be exactly as a as a Espresso, means what I am saying is that Espresso is a heuristic. So difference between a heuristic and an exact algorithm like Quine-McCleskey's or Carnot map, you will always get the minimum size circuit or minimal implementation. But in case of Espresso, you will get minimal or slightly near the minimum value, but speed up of implementation is extremely fast. Like if I give you 100 variable function, Carnot map cannot solve it. Quine-McCleskey will take years to do it because it is an exponential algorithm, but Espresso will solve it in a click, because it is a heuristic and it is very interesting, we will also cover in this course. So that is optimization of the CAD flow, that if you are taking a QM or Carnot map, it will take a long time to automate this flow, because from RTL design, a logic synthesis is the gate level design that nobody will do it manually, they will use an algorithm and a computer to solve the problem. But Quine-McCleskey's or Carnot map is an unoptimized algorithm, as I would say, because they are exponential in nature and they take a huge time to solve it. But Espresso is a heuristic which we can say as an optimization of the CAD, so that you can get a very quick results in terms of gates. So here the optimization in terms of CAD algorithm I can call that as a Espresso. So Quine-McCleskey is a normal algorithm, Espresso is a optimization of that, because it can solve the gate level design in an extremely fast manner. Similarly, so this will also be discussed, all parts optimizations will be discussed, but only thing is that after this part, after the after this first dotted line, it is based on the optimization of the CAD tool, not on the input side. It is on the CAD tool which actually automatically synthesizes the circuit for you. So we will be having good algorithms so that you can synthesize a very good quality circuit and also in a very fast amount of time, because Quine-McCleskey Carnot map can also solve the problem, but they will take years to design a circuit, but heuristics like Espresso will do it in click in a very short amount of time. Then finally there is something called physical layout. Physical layout means the gate level will be implemented in terms of hardware, transistors. So in that case also you should have very good type of placement and routing algorithms, because what happens in placement and routing, basically you have the circuit die is there and you have to put your gates in all the places, and you have to place and layout, you have to place the circuits and you have to make interconnections, because I mean if when you implement, a gate will not look like this, a gate will look like a rectangle and there is lot of Q rows in a die, you have to put the gates in the proper positions in a minimal amount of area, so that you can do the interconnection. So I mean this you can look at any standard backend architecture also will slightly cover this in this course, and basically you are going to get a physical implementation of that. But now what is an optimization here? If I get a very big die, I can put lot of gates and lot of vacant spaces will be there. It will be very easy to place and route it. But now this is a very unoptimized design. So if you want to bring it closer, then I have a very small circuit and I have to put all the gates. But if you make it too smaller, then you may not be able to put all the gates. Routing on may not be feasible. So you should have a reasonable amount of die size so that I can put the gates reasonably. I do not waste too much amount of space. Still I can complete the circuit. So again, nobody can do it manually. There are algorithms to do that. So again, optimization in this case means how you can get a compact layout, but also that compact layout should not take years to be solved. Means from the gate level, I should not take years to generate that compact layout. I should get it in a reasonable amount of time. So I have to have good quality algorithms or optimized CAD algorithms to solve it, as well as the circuit implementation also to be optimized so that I can get a compact circuit. Next is finally the circuit will be fabricated and it has to be tested and sent to the market. So as I told you, fabrication means you can have lot of defects introduced in this stage. So you have to finally manufacture you have to test all the chips one by one, because as I told you, each of the chip can have a fault because yield is generally 60 to 70%. So all the chips have been tested. So very important is something called a test plan. So what is a test plan? So test plan is basically, so how I can basically get good quality test patterns. So what do you mean by good quality test patterns? Because all the chips has to be tested. So if I give 100 test patterns to solve or test a circuit, nobody will take it. I require very good quality 2 or 3 test patterns, because if I keep on applying test patterns, there will be 1 million chips to be tested. So it will take 10 days or 10 years to test the chips. But I require only 1 day maybe to test all the chips and ship it in the market. But on the other hand, I cannot give very bad quality test patterns so that I do not detect the faults at all. So here optimization means good quality test patterns so that you can ensure that all your testing is done, but also the testing should be such that minimal amount of test patterns are generated. And of course, this is actually good quality test pattern and optimization in that direction. But again, test patterns will not also be generated manually. There will be also CAD tools to do that. But if you generate test patterns in 10 years, given a circuit, I say that I am going to give you the minimum number of test patterns to test it, as well as very good quality test patterns I will give you. But to generate the test patterns, I require 10 years. Nobody will take that. So your test generation algorithms also has to be optimized, and that's the CAD flow, and whatever output you are giving as that also has to be optimized in terms of good quality test patterns as well as good quality good quality and faster test patterns. Now, in this entire test flow, everything is about optimization. How can you get a good quality circuit? Optimize in terms of speed, layout, and speed, area, and power, and also the way you are generating it or the algorithms you are generating it has to be also very fast, so that you get good quality optimized output, as well as this process of doing so it has to be optimized. So optimization at all the level. Mainly in this course, as I am again repeating, mainly in this course, mostly in this course that I say, we will try to focus on how you can speed up the CAD algorithms. But obviously, the input part, which is a manual part to be given as input so that you can get good quality circuits out of the CAD, is a manual procedure. So how we can give good quality or optimized inputs to the circuit, to the CAD tools rather, basically that also will be discussed. But again, another very important part which we will be also looking at this course, which will make it separate from CAD for VLSI course, is how we can handle larger circuits like NOCs or SOCs. Standard CAD flow will also talk about the same thing. How can you get good quality inputs? How can you make the CAD algorithm faster so that you can get the circuit designs faster, and they should be optimized in terms of area, speed, and power. But they only talk about circuits generally in the level of gates, because mainly such courses are focused towards circuits of reasonable complexity. But in this course, we are actually trying to look beyond that. We are trying to look at mainly circuits from NOCs, SOCs, multi-core architecture, etc. So basically, what needs to be done? Mainly the key word here is abstraction, that you cannot go to gate level. You have to do everything at the abstract level, like from the behavioral level, we have to look at something for the register transfer level. You cannot go to gate level. So all the algorithms actually, like test pattern generation, testing, verification, design, all we have to do at a very abstract level, so that at least you can handle very large circuits so that it can go to the system level. So another very important part which we learn in this course is optimization in the CAD algorithms or designs to handle very large systems, which is generally not taught basically in standard CAD for VLSI design. So CAD for VLSI courses. Anyway, let us come back. We will now take an example, because lot of theory and open air statements I have made. Let us take an example and quickly learn what is optimization, what we are going to do in this course. So basically, it's a very simple example. We are taking two inputs, out 1, out 2. It is A plus B and C plus D. 4 are the single bit inputs, out 1 or 2 bit output. Some specification has been given to you. Then there is some first step is called high level synthesis. Basically, somebody might have told that I have two bits coming, you have to add them. Very simple specification here, so nothing much to think about, I can directly write this. But in a real case, the general specifications are written in text, there is 100 man hours or 1000 man hours goes to convert it into a implementable or technical specification. Then the next step is called something called high level synthesis. High level synthesis, or sometimes we call it as architecture synthesis, because in this case architecture synthesis is not there. Basically you have to take 2 bits and basically you require an adder to do that, as simple as that. But if it is more complicated, then you have to think, because if I say it for a processor, you can understand that there will be a full manual or a book where these specifications will be written. Then you have to think where I have to put adders, what multipliers I will require, what will be the broad circuit diagram, etc. But in this case it is very simple specification, so you can just think an adder is required. Maybe you can also say a simple half adder will do, because there is no carry business here. But then there is something called high level synthesis. Now from the specification and block level diagrams, maybe I can just think that you will require a block, you will have A, B, and there will be some out, some out and carry. Something will be there, I do not require anything else. Same block level diagram you can think from your mind. But you will not even think that what is maybe, I mean, if I say that A and B are 32 bit, then at least some more impact, means a thought can go over, that will be the ripple carry adder or carry look adder depending on speed, frequency, etc. Okay, so more complexity comes, more complexities or more sophistication will come over here. But as you can think, this is a fully manual procedure for a reasonable, for a mainly practical implementation, because nobody can or no automation can generate from English language to a circuit. That is actually something is that you make an automatic singer or a person who can sing like Lata Mangeshkar, there is an automatic computer, or any reputed singer, a computer can do it. That is not at all possible. It is my understanding that if everything can be automated, that then no, there will be no role of any engineers. That is not possible, but the main crux of it is that what has to be designed and how optimally it has to be translated from an English language to a technical specification cannot be automated. So anyway, so the second step is called high level synthesis. So in high level synthesis, basically such implementation like block diagrams I have has to be written in a abstract language, like we like it system Verilog or C, with some higher level languages we write it, and so that basically they are high level, they actually convert these block diagram specifications into register transfer level circuits. Register transfer level means you have some registers, some combinational circuits, some registers, and that fashion. So that automatically the combinational circuits will be fabricated or will be synthesized in gate level by automatic tools. Anyway, this slide you can read it, but basically an example will make that example will make the things more clear. Then again we can come back to this slide. Say for example, we require something like this. This is actually called scheduling. The high level synthesis means first is the scheduling process, that you have to do A plus B, C plus D. Do I need the answer in one step or do I need the answer in 2 steps? If you need the answer in one step, then both the adders has to be scheduled in step 1, because there is no dependency and it should be generated. Now fine, this is one schedule. Now thing is that how many hardware I have, how many blocks I have. Say for example, somebody tells you that I have 2 adders and 4 registers to do that. Simple, one adder will be there, one adder will be there, a simple implementation will be there. Somebody tells, no, I do not have that many amount of adders, I have basically only 1 adder and 2 registers, I do not have that much budget. Then how do you do it? Then of course your schedule will change. So you have first step you do it, second step actually you reuse the same adder and the registers. First step you put A and B in the register, add it. Second step actually use the same registers, put C and D and get it. Now you have to get the answer in 2 time steps. This is a very simple example, but of course if there is a dependency, like if you say that instead of C it is out 1 plus D is equal to out 2, then even if you have multiple resources, because of this dependency you have to wait for 2 stages. So this is called scheduling. So based on your basically requirements and dependencies, you have to get an optimal schedule. There are lots and lot of textbooks with algorithms which, given the requirement of speed, power, time, etc., they can generate good quality schedules for you. So there are a lot of optimization can be done to generate good quality schedules depending on the resources available and your timing requirement, speed, power, etc. Like this example, if you see, will take more number of adders, but will give you solution faster. Low area overhead, but the time of generation is slow. So this is the first stage of the high level synthesis. So you are going to get from schedule, you are going to get the RTL circuit. Now of course, if I implement something like this, there should be a lot of multiplexing arrangements. This just showed you the block diagram. Finally you are going more real towards circuit. This one is more simple, because 2 independent circuits are there, you just feed the input here, you are going to get it, there is no more circuit required. But if there is this, if you are going for this implementation, then there is a problem. So first time A will go, B will go, you will add it. Second time C will go, D will go, and then you are going to add it to. So you require a multiplexing arrangement to do that. So first the control will be 0. So this one, next stage control is going to be 1. So this stage and this stage. So okay, so you require a controller implementation with this. Now this part basically you can, is an automatic flow. There are a lot of, as I told you, but still there is some manual intervention. But once this is done, how to generate a multiplexer, how to generate an adder, and how to design a register and how to generate an adder is extremely straightforward. There is no manual intervention required. But whether I require this schedule or whether I require this schedule, there are a lot of scheduling tools available which can automate it. But still I generally call as semi-automatic, because there are a lot of schedules available will be coming out of your tools, and then you can select any one of them to decide which one is the best suiting for you. But once you get a register transfer level diagram like this, there is no more manual intervention required, because everything can be automated, because there are just some block level diagrams to gate level synthesis. Now of course this is your controller. I have to generate a circuit for this. So first stage it will be 0 and second stage it will be 1, and it is done. So we call it as the CDFG, control and data path diagram, for your RTL circuit. After that everything is automatic by a CAD tool. So in the first phase, what we are going to just look at this slide, whatever I have told you is written in this slide, you can read through it. So the input to a high level synthesis tool is in some high level language like C system Verilog, that is the top level you will write like this. Then there are a lot of the high level tool first schedules the computations at different control steps. So there are a lot of good quality scheduling algorithms available. So they will give you a lot of schedules, you can take any one of them, or even if you just want to go by the tool, you can take any of the ready-made schedules available for that. But anyway, in this step some amount of user intervention is also required. Following that, depending on the availability of hardware units, constraint schedule computations, that is your scheduled output, are allocated and binded to hardware units like adder, multipliers and subtractors. That is, this part is scheduling, and after that based on the availability you will bind them to exact hardware. In this case, this is possible to go for a single step scheduling, because there is no dependency. But as I told you, if I would have C equal to out 1, that A plus B is equal to out 1 and out 2 is equal to out 1 plus D. So in that case obviously this block will come down. So based on dependency and 7 other factors, you will have some schedules generated, and based on the availability of hardware you allocate and bind them to the operations to the hardware. So once that is done, that is actually called the high level synthesis, which is fairly automated, but still some manual intervention will be required. But after the RTL circuit is gone, it is fully optimized. So what we will study optimization here? We will first see that how can you write good quality high level system C, system Verilog or high level languages to give a good quality of inputs. Like in this case it is very simple, A plus B, C plus D. There is not much you can do over here, but we will see examples today where you can write slightly more, how given input, how you can slightly tune it so that you are going to get a good quality circuit output. So given the specification, the input to the high level synthesis, that is some block level diagrams, how you can write it in a more optimized manner so that the circuit output you are going to get is much better. So that optimization we are going to look at. But as I told you, after this everything is very much automated. So how do you implement this controller? This is nothing but control 1, control 0. That 1 0 1 0 means first it may be a 0, then you can get a 1. So it's up to you how you design it, because maybe it should be something like this. This should be a 0 and this should be a 1. Sorry. It should be something like that. I just made a mistake. So you can say that in the 0 and you can say it's a 1. That means from the first you will generate a 0 and then after some time you will come over here and this stage you generate a 1. So in this case it is 0 0 1 1, just the same way of implement. This is another way of writing. In this case first is in this case it first generates basically your C plus D and then generates A plus B. If you write it as 0 and 1, then you will generate A plus B first and then C plus B, same way. But this is a finite state machine implementation basically for this controller. But as I know, you know, the finite state machines can be very easily directly converted to gate level. So that part is also fairly automated. Now what to optimize over here? That given this diagram, finally I will get a gate level diagram. Like I need to synthesize a mask, register, adder, then this controller. From there I need to create a gate level circuit. So this I want to do it very fast. So here the CAD tool has to be optimized in such a fashion. So given the RTL circuit as input, as a block diagram as input, the gate level implementation can be very fast. So when we will be looking at such problems, such type of issues we will look in. As I told you that if you are going to use Karnaugh map and Queen-McLean's for optimization, it's better that you just go for a heuristic way like espresso, which can give you the circuit in a more faster manner. Okay, so this is what I have written. After the RTL is verified, equivalent system specification logic synthesis is performed by CAD tools. Logic synthesis means from RTL to gate level diagram. So they are transformed into logic gates and flops. So the CAD tool has to be very fast and you have to do it in this manner. After the equations for the circuit specification are obtained, they need to be minimized so that the circuit can be implemented in minimum gates. That is the logic synthesis. That circuit specification is there in terms of adder block, multiplier block, this finite state machine as I have shown you. Carnot map and quick matrix algorithm are standard ways to minimize Boolean functions. But again they are very, very slow. So they have to be made faster by optimization using heuristics like espresso. So in the second part, basically in the from onwards, if you look onwards from RTL to gate level or transistor level implementation, that is your gate level synthesis and your back end, the optimizations will be mainly how to make the CAD tools operate faster so that they can handle very big circuits. So in those parts we will be looking at optimization in that algorithm. Now again important is that everywhere you have to find out the logic synthesis should be equivalent with the RTL design. Everywhere you have to see the equivalence. That is actually the verification. If you look at it, you have to verify that whatever architecture synthesis you have done should be equivalent to RTL. Whatever gate level design you have done to the physical layout, that should be equivalent to the logic gates. So at all these stages, you have to formally verify that what was our translation from stage A to stage B, equivalence should be maintained. That is, it should not be something like I had some x here and while going to the next stage I have implemented something called x prime or y, which is different. That should not happen. They are implementation in a different versions or in different ways like specification, block diagram, RTL, gates, layout, but implementing the same functionality. Only the way of representation is different. So equivalence has to be maintained, and as I told you, in this case we have to do it formally because all possible inputs cannot be given. So here optimization should be in such a manner so that I can do the verification extremely fast and more complete. So this is the example of a gate level synthesis. So the simple adder, as you know that this is A, B full carry, you just require a Carnot map to get the circuit as the output. But if it is very large, Carnot map Queen Mac will not be able to do it. You have to use some heuristics called, as I told you, espresso. Then once the gate level is done, basically you have to, as I told you, you have to fabricate the circuit in terms of layout. So there will be a die, so you will have some rows and columns. So the gates has to be placed, and finally that is actually called the floor plan. Wherever which gates we will put where will be the memory blocks. So broad level placement we do about the gates, which is called the floor plan, and then basically finally all the gates will be placed, which is called the placement, and finally based on the requirements of the circuit they has to be properly connected, which is called routing. So now again tell me what are the optimizations over here. Simple, I require a very compact design because if I have a very large design things may cluttered up and basically you will obviously get an implementation but will be high cost. So I want to put everything together, but it should not be so compressed that I cannot put everything. So I have to get an optimal size die. And of course, the optimality cannot be coming in years. So I have to have a very fast algorithm so that I can get a good quality backend design in a reasonable amount of time. So here we will be trying to see, this course will have a small 1 hour, one lecture will be dedicated for this, which will discuss that what are the placement and routing, how it is basically done, and what it optimizes so that you have a reasonably good quality circuit implemented in a, because this is finally what is going to be fabricated. It may look as simple as very nice gate level circuit like this, but finally the fabrication diagram looks something like this. So one figure we have already shown you in the introductory lecture, which is the 15 minutes lecture we have posted on the site as the introductory part. You can just see how a layout looks. So layout basically has some rows, columns and blocks are over there. So finally I should get a, finally this, it is not as nice as this, it's a die with some rows and some gates are put here and there and some interconnections are done. So finally that should also be in a reasonable space, all circuits has to be, all gates has to be put and finally it will be placed and routed. And again that has to be done in a reasonable amount of time because the placement routing should not take a huge amount of time so that your design speed is higher. So this again backend is fully automated by CAD tools, and the optimization mainly we will be trying to look at in this course is how what are the algorithms to go for this backend design, and basically how they can be made faster so that you can solve the backend problem or physical layout in a faster manner and you can get a compact layout. Now testing. So already I have told you in VLSI design millions of transistors packed into single chip, so they have lot of manufacturing defects. So as the yield is not very high, not like 99% plus, which is generally the case for traditional engineering devices like electric fan and iron. So we all know how to design a fan and iron. So once you design it, 99.9% surety is there, they will do their functionality. So their testing is not that important. But in this case, as the yield is high, so we have to test all the circuits. So obviously testing by all possible combination which is exhaustive is impossible, because n inputs means 2 to the power n and all the devices has to be applied. Verification is still simpler, because you have to just take one version of the implementation, one version of the other version of implementation, and just see whether they are equivalent in the software level, and if it is equivalent you are done. But in testing, yes, chip has to be tested. So of course it is out of question to put off or even think about going for an exhaustive test. So there are lot of optimizations which people have done, which we will be looking at in this course, that people do testing on something called the structure of the circuit, which is called structural test, and people also use something called fault models, that rather than verifying the functionality, they take a circuit and they have a very well known fault model. That means you just need to verify or just need to test that none of the faults from that fault model is in the circuit. Because people have already verified statistically and over years that if somebody can find out that this circuit does not have any of these modeled faults or from a fault set, which is a very, very small subset of the exponential complexity of inputs, then you can be reasonably sure that the circuit is working, and then you can sell in the market. So here what will be the optimization? So just giving that test for this adder. Basically stacked fault model is a very well known fault model in which you ensure that none of the inputs are stacked 0 and stacked 1. So maybe they are finding out whether this line is stacked 0 or not. So if you want to verify that this line is, or test this line is not stacked 0, so you have to put a 1. So 1 in this AND gate means this has to be 1, B has to be 0, so this is 1, right? This is 1, 0 means this I am putting as 1, just I am going to see how it is happening. So 1 means it will be a 0 over here, 0, so this output of the AND gate is 0. So now you can see this is 1, normal case, this is 0, normal case. So output is going to be 0 if fault is there. Because if there is a fault, this 1 will be converted to stacked 0, because this line is stacked 0. So in this case it will be 0. But if the circuit is normal, then it will be 1 or 0 is 1. So if I find a 1 at the output, the circuit is normal, otherwise it is having a stacked 0 fault. Now in testing, you have to verify that none of the line is having a stacked 0 fault. So when we will be dealing in explicit, because we have a full module with 6 lectures on testing, so there we will see how basically this is a more optimized implementation in comparison to exhaustive amount of testing. In this case, if there are 4 input lines, so all possible patterns will be 2 to the power 4. But if you have a very large circuit with 100 inputs, all possible input patterns will be 2 to the power 100. Not even any question or doing it. But it will be later shown in this course that how this stacked fault model is a very efficient manner, in which case we require a very, very less number of patterns, and still we can ensure that none of the stacked faults are there and your circuit is reasonably fine. Now what to optimize here? Lot of things has to be optimized over here. Given a circuit and a fault like this, how can you automatically find out what is the test pattern to do that? And that also will be very fast, because as I told you, I have done something like 0, so I have to put a 1. If I require a 1 at the output of the AND gate, so here I require a 1 and here I require a 1. So this is AND gate, I require a 0. So this backtracking I am doing, and it is a stacked 0, so I require a 1. This is called fault sensitization. So, but you can fairly get an idea that this can be very easily automated using a graph traversal algorithm. But again, it should not take years and years to generate the test patterns for that. You should not do that. It should be quite fast to do it. So one optimization is, even if the circuit is very, very large, how I can generate such test patterns extremely fast. Secondly, test patterns should be of good quality. What do you mean by good quality? Like for example, this pattern can test the stacked 0 fault table. Here you can easily verify that even this stacked 0 fault here also can be verified. Same pattern. The same pattern now can also verify a stacked fault at the output. So this is a good test pattern, because it can test multiple faults. So are there some good quality test patterns which can test multiple faults? Then I would rather take them rather than taking a fault and only dedicated test pattern for that. That I will not do. If there is a test pattern which can test 100 faults, I will take that. So how can we generate good quality test patterns and also very less set of test patterns, so that I can go for faster testing? But again, the test patterns which have to be generated, of course this is by another automatic test pattern generation CAD tools, they should also operate fast, so that I can get good quality test pattern and also at a faster rate. Last but not least is verification, that at every stage you have to find equivalence. Like you have to find equivalence RTL with input specification, gate level design with RTL, gate level design with layout. So every stage you have to find equivalence, because finally you are going from the layout, you are going to implement the specifications, and finally you have layout. So they are implementing the same thing, but there are a lot of translations that have happened in this step. So you have to find out whether they are equivalent or not. This is a pure computer science mathematical problem, because you cannot apply all possible inputs to do it. You have to mathematically verify that whether it happens or not, basically, and in that case it is a very difficult problem to be solved. All the phases till now I have discussed, like design of a circuit with a very, very large circuit like NOC, SOCs, testing an NOC and SOC. is more or less is possible with tools and optimization techniques available. We have reached very high size circuits, but verification is an exception here. Even with extreme amount of research we have done, tools we have, high power servers we have not been able to formally verify even reasonably complex circuits like entire processor in one go. Entire processor, say with 4 cores or 8 cores, we do not have any techniques or algorithms to verify in one go, because it's a more complex problem than all others. So which will actually also have a full dedicated module on verification. In most of the CAD flow, we just see verification of very small circuits, not even the range of ever 2 to the power 20. Basically, we have some state machine implementation, and then we go for some kind of model checking on that. In this course, basically we will try to go ahead of that, like we will be using binary decision diagram so that we can slightly move ahead. Then we will see very abstract level modeling, and we will try to verify at that level. Then instead of verifying the entire system, can I get something reasonable in a certain amount of steps, because generally the bugs, if there are some bugs, they generally happen very early in the design. So in case of verification, we will try to see how fast we can get the solutions, or we are able to verify mathematically. But still, with all this, even we have not even been able to go to very large or complex circuits. This is a very challenging problem. Now the question, why CAD and optimization? Again, just repeating in 2 words, 90% of the digital design flow is automated, so there are CAD tools, we cannot do it manually. Secondly, we want good quality solutions and also in a very fast manner. So CAD for VLSI, actually all these standard courses will tell you some of all the CAD algorithms which work for reasonably complex circuits. But now this course will try to cover all these things basic, and then we want to optimize the CAD algorithm so that they can handle very large systems like NOCs and SOCs. Also we will talk about how the solution quality also can be improved. If I have a very fast algorithm to solve it, but the solution quality is very bad, the circuit being generated is very bad, no one will take it. So our optimization will be making the CAD algorithms work fast to give a circuit solution quickly, as well as the circuit test pattern will also be having the quality. So therefore, CAD and optimization as very requirement or very interrelated terms when we are looking for large level circuits like NOCs and SOCs. So basically, I have just just the motivation from a simple calculator to Google Cruise Control. So that is the jump we have made, and all our algorithms should jump from a calculator to a cruise control system. Now, some specific examples which will tell what are the optimizations we will look about. So this is a very simple circuit I want to design. For input n, output s equal to 0, simple loop for I equal to 0 to n, s equal to s plus I. Basically, this is your block level circuit for this. There is an adder. So basically, is a counter. The counter will count from 0, 1, 2, 3, 4 up to n. This is one input, and basically there is an add, and this is the sum. Basically, is nothing but s, which is a temporary register storing the value. So initially it is reset. So I am not going to the details. It is a very standard simple digital implementation. So initially sum is equal to 0. The counter is also basically equal to 0 or 1, whatever you want to set it. Every time it will add s equal to s plus I. This s will be equal to the value of the counter. It will be stored in the sum. It will keep on doing it till it will keep on doing this architecture. It will, just a minute, let me erase it. Okay. So it will keep on taking the values from the counter, and it will do it till when there is a comparator which compares the counter output with n. So when the counter value is n, it will actually freeze this sum, so that the sum value will be retained and s will have the value of s plus I. Now based on this, you have to design this architecture. This no tool can do it, ideally speaking. This is a very simple example, so there may be possibility, but just think that if it is a slightly complex specification, you have to tell this to me, that I will have a sum, I will have a counter, I will have a comparator, this feedback. After that, basically we know how to design adder automatically, sum register automatically, counter automatically, and comparator automatically. That's everybody can do it. Now this is a design which you have to give. How can I optimize it? Let me just change it slightly. If I say that, because we know that what is a comparator with n will require, there are a lot of XOR gates required. Slightly if I change it for I equal to n to 0, just I reverse the counter. So what I will do is that initially I will load the counter with n. Instead of 0, I will load the counter with n. Directly I can load it from this, the value. Then what is the comparator will do? The comparator has to compare with 0. So what is comparison with 0 involve? A simple AND gate. So if I just reverse the loop, like from I equal to n to 0, instead of 0 to n, I am going to get the same implementation, but if I have to compare something with n, the comparator will be lot of XOR gates because I have to compare with a normal value of n can be say 128. Then you require some XOR gates to do it. But if I say that from n to 0, then you have to just compare when 0 comes, it will be a down counter, cost of up counter, down counter is similar, it will be a down counter, and whenever you get an n, you have to stop it. So comparator with 0 is simply an AND gate. This is one optimization technique which no tool can automate. That is based on the designer's intuition how we can write good quality architecture. So from 0 to n or n to 0, we can have a much simpler design if you are having the implementation from n to 0. This is the and just some very low level diagram for this hardware, and basically you can see that if you are using a counter, so basically if count is equal to 0, this is a down counter. So basically here I am freezing it. So basically this Verilog implementation will be cheaper because if count equal to 0 instead of n. So if I go for n checking, basically this will be a more larger circuit because count checking with n is a lot of XOR gates involved, but count with 0 simple AND gate. Simple, another very simple example is there. They want to generate a hardware, in which case basically you have to take the central block and 1, 2, 3, 4, 5, 6, 7, 8. This 8 block average it is taking. So if you just look at this loop, just you can zoom and look it, they are taking from I to n, j to n, they are taking all the periphery numbers and dividing it by 8. So they are going to generate the average. So if somebody will tell you this point, you have to generate this average. Now say that I want to do it in a moving window. First I will do it for this point, then I will do it for this. This is a moving window concept. Again, if I simply give this as an input, this one raw implementation if I give as the input in a high level language like this, your tool will generate a hardware to do this. But you see there are a lot of redundant arithmetic is involved, right? For example, if I am taking this point, then you have to add only these 3 bits extra because all these bits and these bits basically has already been added. So if you are using a rudimentary high level language to specify a design like this, your hardware implementation will be extremely compromised. But if you slightly tweak the algorithm, that basically if I want to go for this part, only this new bits has to be added, and because this part is already added, you just implement and do it, you will get a faster solution. So this is the impact of coding style in hardware generated. So therefore, the first part, that is from the specification, you are going to generate some high level language, high level specifications you are going to generate in terms of C or system C. You should have intuition so that I can write good quality high level codes so that the ultimate hardware is cheaper, like the 2 examples I have given. So in this course, first we will see optimization techniques at that level so that I can get the final implementation nice. As I told you, if you give garbage to the CAD tool, you will get garbage as the output. If you will give a good quality input, optimized circuit level implementation, the input of the CAD tool also will give you good quality circuits. So first level will be design optimization at the high level or abstract, the specification level or the abstract level, how good quality codes can be written so that you can have a good quality solution at the end. So next is, whenever you are writing some high level tools in C language, basically there will be lot of compilation involved, there will be lot of compilers will be involved, will generate the very log code because you have to finally get the RTL design. That part is, as I told you, semi automated or more or less automated. We will write some C codes like this, okay, and then or simple like this. Finally you are going to get the gate level implementation by automatic tools. So there will be lot of, as we are going to higher level of specification or representing the circuits, there will be lot of compilation involved. So when there are lot of compilers involved, also there will be lot of compiler optimizations coming into picture. Like for example, this is a simple C code. C equal to 7 for I equal to 0 this, yi equal to C star I. But again this requires a multiplier. So multiplier is larger in circuit. If I can do slightly compiler optimization, which is called strength reduction, so the same thing I have written with slight modification with adding one extra variable, I can implement the same thing using adder. You can just check it. This simple standard compiler optimization fundamentals. That is what basically this is called strength reduction, dead code elimination. So whenever you are designing circuits at the gate level, all these things will not come into picture. Now basically what is happening is that you are writing the C codes at very higher level or circuit specification higher. You have to do it because you are specifying a processor, you are specifying an NOC. You cannot do it at the granular level, you have to do it at a much higher level. So there is no question of doing it at the bit level. But whenever you are going at the higher level of the design abstraction, codes has to be compiled and lot of compiler optimizations will come into picture. Like one example I have given you, which is strength reduction. Because strength reduction means you will require less hardware to implement it basically. So one part, few lectures will be dedicated on how you can have, what are the compiler modifications you have to understand, so optimizations you have to understand, so that you can get good quality input specification to the CAD, so that your final design is also good. Secondly, very large circuits, as I already told you, there will be lot of problem in speed, area and power. So you also see how can we actually go for low speed circuits and low area circuits, and how we can lower area, lower power, and how speed can be improved. There is something called basically clock partitioning. So if there is a register and one register is there is a combination circuit. If it is a very big block, this is the critical path and your clock frequency will be less. So various techniques are available. In one case actually we break it up, which is called retiming. So you are breaking the combinational circuit into smaller parts and putting registers in between. So if the combinational circuit is smaller in size, higher speed can be achieved. This is something similar to pipeline architecture. So some modules or some lectures will be dedicated that how we can write the circuits. Mind, they are all the parts where the design is being optimized, but because as human we are specifying the design requirements at the top level of the specification and high level specification. They are not automated. So at this level we will also look at optimization for speed, power and area in terms of how we can have retiming the circuits, how we can actually have low power, low switching so that the power is reduced, what we can do like in this case so that the area is optimized, like in this case I have shown the area will be optimized. These parts cannot be automated in that, in quote unquote automated. They have to, because they are all engineering problems and they are art, so basically this has to be done by the engineers. So the first part of the lectures in this course will be looking basically optimization from the design level, which is given as input by the engineers or designers at the high level specification. Next, once the RTL is given, there is a gate level synthesis. From now CAD starts. There is very little intervention of the engineers. So from a circuit like this, this way, this way, this way, a circuit has to be designed. So from the RTL you have to get a gate level specification, gate level output. It's very simple. There are automatic tools to do it, because as I told you, Quinn-McCluskey solved this problem, Carnap map can solve the problem, but again if the number is very high, there should be heuristics. So in this case we will study a heuristic called espresso, which actually solves this problem in a very fast manner, because everywhere you require optimization. So in this case the optimization is in terms of the CAD flow and not in the terms of inputs or outputs, because you have to get a smaller circuit in a very fast manner and this process is automated. So that automated process or CAD has to be optimized, so that we will study in the gate level optimization, gate level synthesis optimization. Then again nowadays there are a lot of variations, so that either you can fabricate your circuit in ASIC, and nowadays FPGAs are coming up. So now we have very large size FPGAs, so even processors can be implemented and validated in FPGAs. So few modules will be dedicated where we will try to see basically how you can have a optimized design if you have an FPGA in place, because FPGA is not a gate level block. There are something called LUTs, ready-made blocks like digital signal processing blocks, RAMs, some dedicated blocks are available. So say that I require a multiplier, you need not synthesize the multiplier, multipliers will be available. You have some digital signal processing block, already they are available, so you can directly map it there. Given those fixed blocks, how the other parts can be optimized. There is some technology which is recently coming and not too much discussed in normal CAD for VLSI books. So in this course there will be also dedicated lectures on FPGA synthesis optimization, that given, because in ASIC or normal CAD everything has to be fabricated. Multiplier means you have to have a gate level multiplier, DSP means you have to implement the DSP, but in FPGA instead of basic gates there is something called LUTs, because FPGA is some kind of generic architectures available there in terms of LUTs. You just need to do the interconnection so that you can get a circuit. So basically it is called a field programmable gate array. The same thing can be used for adder, multiplier. Tomorrow you can implement a processor, day after tomorrow you can make image processing block, because you do not require any fabrication for that. So that is now very popular, because to get a fab, hold to a fab and fabricate a circuit is a very expensive procedure. So as complicated or very sophisticated FPGAs are available which can fabricate even very large circuits there, so a lot of market is coming into picture. If you talk about academic institutes, more than 99% of the academic institutes believe in case of digital design, FPGAs, because students can fabricate, they make error, they can erase it. Even in the industry level you are allowed to make mistakes, you can check, you can prototype and verify. So therefore FPGA is also very important apart from ASICs. So a few lectures will be dedicated that what things will change or what optimizations are required if you are thinking about a FPGA based design. Now coming to test. So what do we need in test? We require good quality test patterns, that is multiple faults and minimum number of test faults, etc. And also you should able to speed up the sensitize, propagate and justify approach. Basically sensitize, propagate and justify approach means test pattern generation time. Test pattern generation time. So you have to speed it up. Given a circuit, the CAD tool will tell you what are the test patterns for that. So I need to optimize the CAD algorithm so that given a circuit I get the test patterns very quickly. But again, in terms of solution generated by the CAD tool, like for example, if the circuit is there, we call it cut. This is your CAD flow. This is your test CAD, which is actually sensitize, propagate and justify. It will give you lot of basically your test patterns. But given a circuit, this has to be very fast. That is one way of optimization. That we will see that how I can go for doing it very fast. Secondly, the test patterns to be generated should be quality. That there should be some patterns should cover multiple faults. From different type of fault model should cover. Stacked fault we have discussed. There are other faults we will be discussing in the lecture like bridging faults, delay faults. So can there be a minimal set of patterns which can do all the testing in one go? Because as I told you, one fault, one pattern. I am not bothered to take that pattern. But one one pattern, 10 faults. I am very happy with it. Because if I apply one pattern, 10 faults will be detected. So I need better quality test patterns. Finally, there are other ways of optimization because I want to compress the test patterns and put it so that I do not have to use too much power of the testers. Then again, as I told you, if we do everything at the gate level, things are not going to scale up when you are going for high level implementation like NOCs and SOCs. So we will talk everything at the higher level of abstraction. Like we will not even go to gate level, we will talk about register transfer level, high level decision diagrams and try to solve the testing problem at that level. That is, we will not even give the input in terms of gates, rather we will give very high level inputs of a circuit. We will try to generate the test pattern from that level. So it will be very fast. This algorithm will be very fast, but of course there will be slight compromise in the test pattern quality because everything is very much well verified at the gate level in case of testing. But if you do not give the circuit in the terms of gate level as input, you have to go at a higher level. Then you will get to get test patterns, but of course there will be slight compromise in the test quality, but the time required to generate the test pattern will be very, very high. So we have to, the optimization is that how can we do it will also be covered in this course. There will be one dedicated module, one test. Finally, as I was saying, is verification, model checking or formal verification. There is some specification in terms of what your design intent has to be there. There has to be a formal model of the system, which will be in terms of finite state machine, Buki automata. These are extremely, as I again thinking, the other parts are mainly related to VLSI design, circuits, gates, all those things. But whenever you are talking about model checking, this is more of a theoretical computer science perspective. So whatever circuit or you have designed has to be first represented using a formal model, and like a finite state machine in a very broad language, and there will be some specification that is what you wanted to design, that also has to be written in terms of some CTL or LTL formula, for mathematical formula. Then there is a verification tool which will tell you whether your model matches the specification, or if not they will give you a error trace or a counter example so that you can go and debug it. Look very nice, but in fact it is an extremely complex problem because finite state machine, a system with 20 variables, even you cannot model this machine, it will blow up. Then the verification tool, there are a lot of complications like you have to reach the fixed point, etc. So even if your model size is very large, you cannot do it. So here we will, in this course we will try to, the whole course on model checking will be seen how we can actually optimize this model representation. Do you require to explicitly do it in state space like finite state machine which is exponential complexity, or can you use some type of intelligent methods like binary decision diagram, symbolic model checking to lower this up. So here the optimization will be mainly we will try to see that how we can actually bring down this model, because if you have a 10-bit counter, so you require 10 flip-flops, state space is 2 to the power 10. So but 10-bit counter, as you know, is maybe only very minute part of a circuit design. So very large system is main killing part will be the modeling itself. But anyway, you should have a formal model because it's a formal model checking, mathematical. So you should have a graph and all those things in nature. So how can we represent this in a more optimized fashion so that we can get the answer yes or no in a very quick fashion. So that optimization in representation and model checking will be fully dealing, so that basically we can reach to reasonably complex circuits. But again, as I am telling you, compared to design and test, optimization is still at a nascent stage compared to the complexity it can handle, because you can really design NOCs, SOCs, you can really test NOCs and SOCs, but if you take the entire NOC together, no model checking tool even with optimizations will be able to handle it. So basically we partition it and then try to verify bits and pieces. So a lot of work has to be done in case of optimization. Basically this is the course plan. So first we will go for introduction, and basically which is lecture 1 we have already done. Then there will be high level synthesis will be told to you. Then there will be RTL optimizations, that is how can you give a good quality high level input so that you get good quality circuits. Then logic synthesis and physical synthesis. So logic synthesis means from this part actually you can say your CAD tool comes up. This is how to write good quality codes or good quality circuits to be given to inputs as to the CAD as that is good quality circuits, optimized or good circuit quality input you have to give. That is high level description of circuits. From here CAD starts. So how can you take a circuit and generate gate level in very fast manner? Then there will be entire module on testing. So given a circuit, how can you generate optimal test patterns and in a very fast way. This is also more or less by fully by CAD tools. This verification that is also by mainly by CAD tools. Just the model you have to write, the FSM you have to design, and the specification to be test tube design. After that there is a model checker which will tell whether the specification is met or not. But again at every point we will be looking at optimization. In case of verification, as I told you, optimization will be how we can have a minimal representation of the system and do verification. Test means you have to generate basically faster solutions, faster test patterns, solutions has to be generated for a circuit, and also good quality test patterns has to be done. And again as I have already told you. So basically this brings us to the introductory part of this course, and I think I have been able to make clear to you that what we will be expecting out of the course, what is optimization and what has been automated and what will be optimizing in the automated CAD tool and what will be automating in the design part. So that gist I have tried to give you in the lecture, in this introductory lecture, and I welcome you all to this course. From next lecture onwards, we will be looking into more depth of the concept we have discussed. About assignments and basically your notes. So every week we will be finding out some assignments, you have to solve them in the portal, and basically also some notes and the PPTs will be uploaded to you so that you can also get the reading matter from them. And as you will find later, this course is slightly oriented towards research, because many topics are all very emerging and we cannot cover everything in this 20 hours course. So basically we will give you some references and papers which will not be exactly required for your exam purpose, but will be required for you to carry research in this advanced CAD flow. So all these links will be given in proper time. Thank you.